Hello everyone. Welcome to what will be pre-lecture 2 for our lecture that will be on Wednesday, August 24th. So this is what you should know by the end of this class. I'm not going to be reading through this just because you'll have access to the text as I post the slides on Blackboard. So a good place to start for Principles of Chemistry 1 is trying to answer the question, what is chemistry? And so chemistry is all that matters, we could say. Specifically, or more specifically, it is the study of matter and energy and how it moves between atoms. And one of our big questions in this first unit is going to be, what is an atom? And so an atom is made up of a nucleus, this sort of center part here, that contains positively charged protons and neutral neutrons. Around the nucleus, forming a sort of cloud, are electrons that exist in and move between things we call orbitals. And in chemistry, we're mostly interested in the movement of electrons between atoms and how they might bond. Some other things I'll point out here are that our proton and our electron have the same but opposite charges. So again, electron has a negative charge, proton has positive. And then also, protons and neutrons have nearly the same exact mass, whereas electrons are a lot smaller and a lot lighter. Okay, so when we're going to be calculating atomic weights or atomic masses later this class even, you count protons and neutrons as one atomic mass unit, and electrons do not count towards that. Okay. So another good question is, what is matter? Since we're concerned with studying matter and studying energy in chemistry, what is matter? Matter, very basically, is stuff. And more specifically, it is defined as anything that has mass and occupies space. So in chemistry, we tend to divide matter up into different categories to better understand it and describe it. One of the key ways we identify matter is as elements, and elements are the things we find on the periodic table. We define them as substances that contain only one kind of atom. So for example, in this figure on the right here, we have carbon atoms and we have oxygen atoms. Those are two different kinds of elements. And of course, these elements can combine in different ways, where we can have carbon and oxygen atoms come together to make something like carbon dioxide, where we have one carbon, two oxygens, or carbon monoxide, where we have one carbon, one oxygen. We'll talk a little bit more later about how we name compounds, but they contain more than one element, combined in some sort of fixed proportion. So for example, if we had 3 molecules or 3 compounds of carbon dioxide, we'd have a total of 3 carbon atoms and 6 oxygen atoms because we know the proportion between the carbon and the oxygen. Okay. Another way we classify substances in chemistry, or classify matter, are as mixtures. And so we can have a homogeneous mixture, and those are uniform with the same composition throughout. Something like soda pop is a good example where we have a mixture that you can't really tell what the separate parts are, despite there being multiple parts coming together into a mixture. Heterogeneous mixtures do not have the same composition throughout. So for example, here we have some sand that is suspended in water. We can tell some of this is water, some of it is sand. That is a heterogeneous mixture. Coffee is a tricky one. Coffee is actually a heterogeneous mixture. So particularly when things are dissolved, they are homogeneous, but with coffee actually has fiber, which are things that are not dissolved in a liquid. So coffee would be a heterogeneous mixture. Okay? All right. So when we want to describe elements, we often want to use shorthand to save both time and space. And so in chemistry, we use atomic symbols very frequently, and I've already shown you some. Some of these are pretty easy to remember, and you've probably already heard of. Something like hydrogen or carbon is H and C, oxygen is O. You can get into different elements. Aluminum is Al, chromium is Cr. These are all fairly logical, right? Even something like zinc is Zn, right? Pretty easy to remember. There are, of course, some elements that are not so easy to remember or maybe don't make as much sense. Oftentimes it's because these are derived from other languages other than English, and so their atomic symbol letters do not match how we would pronounce things in English. So, for example, iron is Fe, right? Lead is Pb because that's what it used to be called in Latin. And so I will say you don't need to memorize any of these elements for class, but getting to know them would be helpful. Okay? So elements can be bound to each other and still be considered pure elements. So for example, the oxygen that we're breathing right now is O2, which has 2 oxygen atoms bound to make an elemental compound. Phosphorus can make P4, sulfur can make S8, and you get all sorts of different examples of elements that are also molecules. So how something exists at a standard temperature and pressure, essentially how we would find it in a room, is often referred to as its elemental form. And these different elements can make different arrangements of their atoms called allotropes that have very different properties but still be a pure element. So for example, graphite, basically pencil lead you use to write, is pure carbon arranged in sheets. And if we rearrange that pure carbon into a different pattern, this hexagonal or cubic pattern, then we would end up with a diamond, which we know is very different than graphite. Okay? All right, I believe the last part for our pre-lecture here is going to be talking about what's inside an atom. So we have protons, neutrons, and electrons, right? And we talked about how a proton is a +1 charge, an electron is a -1 charge, and protons and neutrons in the nucleus have essentially the same mass and are what contribute to our atomic mass. So despite almost all of our mass being in our nucleus, it only occupies about 1/10,000th of an atom's volume. So this would be a representation of an atom here where we have the nucleus in the center, and this would actually be bigger than the nucleus would even appear when the rest of our space is filled by an electron cloud. And we're going to talk more about that next week, so hang on to that idea, but our electron orbitals make up the majority of the volume of an atom. Okay? We can also identify these elements as they appear on the periodic table, and typically they're organized by atomic number. So that's going to be this upper left-hand corner here in this representation of the periodic table tiles. So for example, carbon is atomic number 6, and we know that that is representative of the amount of protons it possesses. And so that is going to be its atomic number. Each element also has an atomic mass, which we're going to talk about in class and a little bit next class. That is an average of all of the masses of different isotopes that make up an element. And a little bit more on that. So the atomic mass is a weighted average there. And so let me define what an isotope is. It is when an atom has the same atomic number, so the same number of protons, but has a different number of neutrons. So for example, if we look at carbon, carbon can exist with 6, 7, or 8 neutrons. And we would denote that using this notation here, where we have carbon-12, carbon-13, and carbon-14. In any sample of carbon we would take, our natural abundance, or the percentage of isotopes, so 98.892% of those atoms are going to be carbon-12, 1.1% approximately is going to be carbon-13, and only 1 in 1 trillion of those atoms is going to be carbon-14. And essentially we can take a weighted average then of the isotopes, and that is the mass that then appears on the periodic table. Also, I really like that there's a AAA baseball team called the Albuquerque Isotopes. So I show their logo here. And they are, of course, my favorite minor league baseball team. Finally, we have ions, and so isotopes have differing number of neutrons, whereas ions have a differing number of electrons. So cations are positively charged, anions are negatively charged, and they tend to form nonmetals. So ions are formed through the transfer of electrons, which produces a different form. So for example, up here we have table salt, NaCl, sodium chloride. This is what pure sodium looks like if you put it in water, right? It's basically lights on fire. And so it's a very different property when it has that one extra electron. Okay, that's going to conclude our pre-lecture for today. Hope that was good, and I will see you in class.